Okay, in this short video, I'm gonna talk about the last topic of the day called random forest. Okay, random forest is a special case of the bagging algorithms. It's based on the boosted random sample, but the random sampling isn't random enough. Isn't random enough. With bagging, often the decision tree look very similar. This is because with bagging, often the decision tree looks very similar. This is because if data contains one very strong, very influencing strong predictor. Okay. So same feature will split at the top for every tree. So this implies same feature split at the top of every tree. This makes the trees very, very similar. And random sampling does not change that. If the trees are very similar, then taking the average of the similar tree does not reduce the variance much. So we need to further reduce the correlation between different trees. We need further reduce correlation among different trees. How do we avoid such scenario? How do we avoid each time we train our trees using the strong? How to avoid each time we have the same set of the strong predictors? So in this case, we not only we introduce the random sampling on the samples, but we also random the features. Okay, so the idea random forest. At each tree node, take a random sample of m features. Take a random sample of size n prime and m features. So not only we take a subsample, we also take the random features. Taking the rows, we sample the columns too out of D features. And then we choose the best split among M features. Then choose best split from M features. In general, how do we choose this M and how do we choose this? For classification methods, I think there is a paper talk about the best number of the feature is the square root of the sample size D. Feature size D works well. The sum of the rule for classification. Okay, and for the regression problem, we choose D over 3 for regression. Works well for regression. So if you, for example, if you have D equals to 100 features, you can randomly choose 10 features. Features, and then pick the one of those 10 in the best and two best split, and then to further train the regression trees. Choosing M, you can think this M is a hyperparameter. You can tune in applications with validations, cross validations. And a smaller M means more randomness, and the tree less correlations, more bias. So smaller M means more randomness. This means less tree correlations. And one reason this works is if there is really strong predictor, only a fraction of trees can choose that predictor as a first split. And that procedure gives many decorrelated trees. And that means when you take the average of these trees, the average will be less variance than the single trees. Usually this method gives the very good test error. Okay, so random forest will give better test errors. Dramatically compared with the single trees. But the disadvantage is it's relatively slow. It's slow. And it lost interpretability. Loses interpretability. and you don't have that statistic inference. For example, you lose the ability to make the inference. For example, to measure the uncertainty of the prediction, the probability you make, how likely, even you make the prediction, sometimes people cares about how likely you're gonna make this prediction. So, but if you use random forest, you cannot make the inference. Maybe I think that's all I want to talk about today. Maybe I also have few videos I want to show you that different bagging methods. For example, this is the you're bagging on different support vector machines. Okay, and we can see after we taking the average of this, we can get the random decision boundaries. And also we can see the trees with different depths. Let me see which one. By taking the average, we can. Oh yes, this is a decision tree and with different decision boundaries. With different tree depths. Let me show you one more time. This is with different trees, okay? And then we take the average. For example, we can get a very nonlinear. For the classifications, we can get a very nonlinear and smooth decision boundary by taking the average. Okay, this is another scenario. And even for the very complicated shape, we can do the classification well. For example, this is like a like a spiral data. This classifies the spiral data. Each forest takes the advantage of the training using the 400 trees. The bottom tree, and here we have the 12 trees, 12 shapes. So even you have very complicated shapes, by the random forest, it can doing very good job, much better than the support vector machines and the logistic regressions. Okay, I think this is a depth. This is a regression tree with depth 4 and depth 12. Which one is 2? Oh, yeah. On the left hand side is depth 4 regression with depth 4. On the right hand side, we require the maximum tree to be depth 12. Even with the weak learners, as we require the regression tree to as deep as only 4 depths, it works pretty well. Okay, I think that's all I want to talk about today. And the next class, we're gonna move on to a new topic, kernel tricks, and then we're gonna cover some about deep learning neural networks. Okay, thank you.